All right, let's start again. So my name is Paul Dütting. I'm an associate professor in the Department of Mathematics at London School of Economics. And I want to cover the second half of our tutorial on contract theory, a new frontier for AGT. So by the way, are you hearing me all right? Good. So what you saw in the first half was the basic model of contract theory, which was this hidden action principal agent model. And you also saw, kind of the basic design question, namely that of designing optimal contracts and how it can be solved using linear programming. And Inbal told you a bit about some of the questions that economists looked into, in particular, trying to find regularity conditions under which this optimal contract that comes out of this approach has natural properties such as monotonicity. My goal in the second half will be a bit different, so we call it modern approaches. So I basically want to give you a, of course, very short and rough introduction into what I think could be a modern theory here, which also leverages ideas from algorithms and computer science to advance the theory, contract theory. And I want to do this by looking or focusing on three different topics. So one is robustness, one is approximation, and one is computational complexity. Each of these aligns to kind of what I think what the high-level contributions of computer science to economics are. Okay, so let me jump right into it. So the first thing I want to talk about is robustness. And what you saw in the first half, and this is a kind of well-known criticism of this whole model and approach, also well-known to economists, is that this classical principal agent model due to Holmström and Grossman and Hart, it's nice mathematically, you can write down the optimal contract, but one thing that's a bit unsatisfying is that the optimal contracts that come out of this, they tend to be complex and intransparent. They're solutions to LPs, and they exhibit undesirable properties such as non-monotonicity unless we impose really strong and not really realistic assumptions. And I think maybe most importantly, they don't resemble at all or don't look at all like contracts that we see in practice. So what do we actually see in practice? I guess that's debatable, but I would generally say that the contracts that we see in practice, they tend to be simple, and often they have a linear form. So what's a linear contract? So this was on the slides in the first half, but Inbal went over it quite quickly. So it's a very natural idea. Namely, it's just a commission, a linear commission or fraction. So whenever an agent's action results in a certain outcome or reward, you just pay the agent a fixed fraction of that reward, say 25%. Okay, so technically it will be just the following linear function. So the remuneration or payment that we want to make upon seeing a certain reward R will just be alpha times R, where alpha is some fixed in advance number between 0 and 1, like 25%. Okay, and this is super simple. In particular, it's just a single number that specifies my whole contract. Okay, now the kind of really classic reference on this work, also on the slides in the first half, but Inbal didn't really get to it, is a paper by Milgrom-Holmström, which is really nice. So what they do is they look at a dynamic version of this contracting problem in which the agent and the principal interact in a repeated fashion, and it's sort of a dynamic model underlying it, which I don't want to go into too much detail. But one of the conclusions of their work is that in this slightly different model, actually linear contracts turn out to be optimal. Okay, that's kind of the one citation that you would make if you would want to argue that linear contracts are good. But I would say, or at least in my reading, that the two authors here, that they themselves were not really satisfied with the result that they got. And I added this quote here to sort of substantiate this claim. Let me read it out. So what they write is in their paper That's probably the great robustness of linear rules based on aggregates that accounts for their popularity. That point, however, is not made as effectively as we would like by our model. We suspect that it cannot be made effectively in any traditional Bayesian model. Right? So we're somehow alluding to robustness, some unhappiness about the model or the fact that they had to move away from the classic model. And I think most importantly, and almost visionary, they see this fundamental barrier, namely this inherent thing in most of econ approaches that it's Bayesian, so an average case analysis. And in fact, if you look at the literature from 1987 onwards, the econ literature really struggled to find strong and convincing arguments in favor of linear contracts. Okay, I mean, it was an active field of research, and there are papers, so I don't want to do them wrong, but I think generally the agreed opinion was that there was a lack in the model, in the theory that we have. So this changed, I think, recently with a very nice breakthrough result by Carroll, and this is what I want to show you next. So it's a 2015 paper. Okay, so that's Carroll's model. So it's really working in the original model, right? So recall that there we had this notion of an action AI, which was specified by this distribution. So the probabilities that it puts on each of M rewards are J, and each such action also had a cost Ci, right? So the basic vanilla model that Ian will describe to you. And what Carroll does, he only changes one aspect of this whole model, namely, that's what I tried to illustrate down there, I mean, the assumption here is that the agent has a set of actions, which will be denoted by this calligraphic A, but, and that's the new thing, the principal only knows a certain set of action, A0 or A0, and the actual set of actions that will be realized in the problem is a superset of this, and this superset will be chosen actually adversarially. Okay, so it's forthrightly non-Bayesian, right? It's worst case in a sense. So what are the implications of this innocuous twist to the model? So let me just walk through more or less the same slides that Imber had on the timing and what the agent and principal are trying to optimize. Okay, so there's not really much that changes in the timing of the problem, except for the two things that I've highlighted in red. And if you want, you could also add in the point in time where the adversary jumps in. Okay, so as before, the timing is as follows. So the principal has the initiative. He sets up the contract. But this time he sets up the contract only knowing A0, A0. And he offers this contract, which is again kind of a payment contingent on the actions. Okay? And then if you want right after this, the adversary jumps in and writes down all the possible actions that there are, which is a superset of A0. And then things flow naturally as before. So the agent would accept the contract. It would take a hidden action now from this larger set. So that's why I highlighted it in red. And then as before, the agent's action triggers stochastically an outcome or a reward, which goes to the principal. And the principal, in turn, pays the agent according to the contract that he committed to. Okay, so that's the model. From the agent's perspective, things are fairly easy, right? So, I mean, he's at the point where the contract is specified and the set of action has been written down. So quite naturally, what the agent will do, and I'm using here a mix of Inbel's notation and the one from Carroll's paper, but it's really just simple, right? So the agent, what would he do? So he would simply choose the action A star from the set of action he's allowed to, so A, that maximizes his utility, and the utility is simply the expected transfer that he gets minus the cost, right? And this A star will be one of the maximizers here. And in particular, this will imply, so any such action A star, this maximizing set will imply a certain agent utility. So that's where I'm adopting Carroll's notation here. So I will write VATA for this. So it's the value, if you want, of the agent for the contract or under contract T given set of actions A. Okay, notice that from the agent's perspective, there's sort of some notion of a reserve utility, reserve agent utility that he can achieve, right? Because, I mean, for the problem above, he's maximizing over all possible actions A from this larger set A. What he could do instead is just optimize over A0, which is a subset of A, and this will be a lower bound on the utility or value that he can achieve. Okay, so now to the more interesting part. So what is the principle trying to achieve, right? So he's designing this contract only knowing A0, but then later on, some larger set of actions A will be realized, okay? So since the principle's payoff depends on what the agent does, it will be convenient to define this first thing here. So this set A star, which will be the set of agent actions that give the agent the highest possible utility under this contract T and the set of actions A. Okay, so that's what I will call A star. And then what I think what's a very natural thing the principle could do here, I mean, what he could do is, of course, he could try to design a contract that's kind of max min optimal, right? So given his knowledge, he tries to find a contract, so that's the max part, that gives him the maximum minimum utility over the set of possible actions A that the adversary can choose. Okay, and that's just what I wrote down there, right? So this latter part here is just the principal payoff. So in analogy to the agents, I will write VP, so value of the principal for contract T under action set A, right? And I mean, it's a bit nasty to write down because the agent has to choose an action, but otherwise it's simply reward minus transfer and expectation. And he tries to take the best of these. And let me call VP the solution to this. Okay, so that's the maximum problem. And in a sense, what the principle now tries to do is tries to find the max-min optimal contract. Okay, and I think it's quite instructive to draw the analogy to the previous slide, the agent. The agent had this reserve utility that he could just maximize over the set A0. There's some similar notion of reserve payoff for the principle that he can achieve. Okay. Turns out for an arbitrary contract, there is no such notion. But for the special case of linear contracts, there's actually a very natural way of getting a lower bound on the agent payoff that only depends on what we know, so this A0. Okay, so let me do this. And here the key insight is this pi intuition, namely that with a linear contract, recall it's just paying an alpha fraction of the reward. For any possible action, you actually split the expected welfare in an alpha and 1 minus alpha fraction. Okay, so what do I mean with this? So the expected transfer, that's the first thing, right? So that's the expectation of T of R. Of course, that's simply just alpha times the expected reward, because T of R is just alpha times R, and I can pull out the alpha. And similarly, the expected reward to the principal, so reward minus payment, will be just 1 minus alpha times the expected welfare, right? Just using the first, right? So if you view this expectation of R as the expected welfare, then it's split into alpha and 1 minus alpha between the two. Okay, now this will allow us to derive a lower bound on the value that the principal can achieve, right? So what's the value that the principal can achieve, right? So it's this expectation of R minus TR, right? So this thing here, so it's 1 minus alpha, the expectation of R, and this we can express in terms of T of R by just dividing or bringing the alpha to the side. So this gives us 1 minus alpha times T of this, and if we replace this with T of R, we get divided by alpha times the payment. Okay, now I can lower bound this, right? So it's the expected transfer by just subtracting the costs. And now this term you recognize as the agent utility, and in particular, this is lower bounded by this previous derivation on the agent utility, very roughly, right? So in particular, we get a lower bound on the principal's payoff, which depends on alpha and the agent utility. And it turns out that maximizing this lower bound over alpha, that's the optimal so the maximum optimal contract. And in particular, it's a linear contract. Okay, so that's what I wrote here. So that's the theorem. So for all partially specified principal agent settings with rewards R1 to Rm and a known action set A0, there exists a linear contract that maximizes the principal worst case payoff over R, all possible extensions A of A0. Okay, and I gave you the form. Statement clear? Yeah. So this right-hand side. Okay, and I want to give you, so that's just that a linear contract suffices. What I claimed before was the specific form of the optimal contract. So let me just convince you that linear contracts are optimal. So what's the proof ID here? And I just want to give you a vague geometric intuition. I think it's nice. So the two key steps in the proof are, first, that if you start from any not necessarily monotone contract T, that then there's an affine contract T prime with the same or better worst case guarantee. That's what I want to show you next. So affine would just be alpha times R plus beta. And then if you have such an affine contract, then you can always further improve it to a linear contract T prime prime. That's straightforward. You can check the paper for details. Okay, so let me give you the intuition why affine is good. Okay. So here's how I want to argue this. So I want to start from an arbitrary contract T, and I want to argue that an affine contract is not worse in the worst case payoff metric for the principal. So let's do the following. So let's plot on the x-axis the possible rewards, and then on the y-axis the respective payments that we make. Okay, so any contract I can write down as such black dots. In this case, it's not monotone because it's jumping up and down as we go from left to right. Okay, now for any action A, which is defined by a distribution in cost, I want to look at the points consisting of the expected reward of that action and the expected payment of that action. Okay, and then clearly all these points must lie in the convex hull here, right? Because on the x-axis we have the rewards, right? So the expectations will be just convex combinations of this. On the y-axis we have the expected payments. So again, it will be convex combinations of these. So we must be within this shaded gray area. Okay, moreover, what we know is that, so I told you about this reserve agent utility. So agents will only, of course, accept actions that give them at least this payoff, right? So in this picture, this would translate into some kind of lower bound or floor below which you won't accept any points, right? So that's the dashed line. So we're looking at these dark gray area. And now in this dark gray area, let me switch to the principal's perspective. What's the point in this dark gray area that's worst for the principal? So recall the principal is trying to maximize reward minus transfer. So that's 45-degree angle. Level sets will be orthogonal to this. So except in degenerate cases, it will be the lower left corner of this area, the point Q. Okay, now from here it's quite easy to go forward. So I want to look at the support line through Q on this convex set. Call this T prime. So this will be my affine contract. I am claiming that the worst case payoff of this new affine contract is no worse than the one before. Okay, and now to conclude the proof, from here you just need to argue that you could further improve by going to a linear contract. Okay, so it's the geometric intuition. Okay, it's recorded so you can rewatch. Okay, so I think super nice result, right? It's a very clear model. It's non-Bayesian, so I'm very appealed to it as a computer scientist. And it's a strong argument in favor of linear contracts. But I would say, obviously, it's not the only way in which one can formalize model uncertainty. And being a computer scientist, you may think that this notion of any possible extension of actions is maybe less natural than what you would have thought of if you were to write this paper yourself. And in particular, I think there's one assumption that's very common in computer science. If you look at problems with a stochastic ingredient and you want to be robust, then what we often do is that we assume that the details of the distributions are unknown, but maybe that you know the first and second and so on moment of the distribution. I think that's another natural notion of robustness that one could study in the setting. And indeed, this has been done in computer science and OR since quite some time. I think the first reference that we could find was this seminal paper by Scarf on robust stochastic programming. It has been looked at in prior independent auction design, so in AGT. So is this maybe a potential way in which, like, a computer science perspective could add to the model, to the literature? And indeed, in an EC'19 paper with Inbal and Tim, we looked at exactly this question. So basic principal agent setting. We have a fixed set of outcomes as before. So this should be R1 to Rm. We have n actions with costs, C1 to Cn. But now we assume that the details of these distributions are unknown and that we only know their expected rewards, so that these Ri's, as we called them before, are known, and we will call all possible F's that match these expected rewards compatible distributions. And what we show is that for every such contract setting with known expected rewards, linear contract again maximizes the principal's expected payoff, in the worst case, over compatible distributions. That's a good question. I mean, what would you use then in order to? I mean, what would you, I mean, I don't even see how you would optimize if you don't know anything. Yeah, but maybe, yeah, but there are certainly many other ways, I mean, assuming limited information where you could ask similar questions. But maybe to continue, so what I want to emphasize here is that we get the same conclusion that Carroll got under a very different hypothesis. And I think that significantly strengthens kind of the conclusion that linear contracts are good. And I encourage you to come to the EC talk this week to see more about the proof and this result. Okay, so Inbal promised open questions. So I think that was a first, hopefully, illustration of how kind of a more CS optimization perspective could add to the literature. I think open questions here would be, first, kind of, is there kind of a unification of Carroll's and our result? There are, of course, other models of uncertainty. So you asked, what if I don't know anything? Another question could be that you maybe know the distributions, but not exactly. So maybe up to some error. What can you do then? So this has been done in auction design and in pricing before. And more generally, I think that this whole area of maximum robustness is something where there's some interesting work going on, both in economics and in computer science. So we saw examples of contract design, so in particular Carroll's paper and our upcoming EC paper. But there's also a very active stream of research on revenue maximizing auctions under the same assumptions. And there's also one EC paper upcoming this week on profit inequalities under this model. Okay, so it's kind of the first direction, which I think is interesting. So let me talk about another one, namely approximation. It's something that computer scientists have used in signaling and mechanism design. Can we do something similar for the contract world? Okay, so I guess most of you are computer scientists, so you know this, but let me quickly recall. So the idea here would be, I mean, quite generally, so if you have a microeconomic mechanism, maybe a simple one, that's potentially suboptimal, can we somehow provide guarantees how good this is? And of course, one possible way of doing this would be to bound the worst case performance loss, either multiplicatively or additively. So for a maximization problem like the one we're facing here, we'd like to find the largest delta in 0, 1, such that our performance of the simple mechanism, contract in our case, on this instance is at least some beta fraction of the optimum for all possible instances, right? And of course, we want beta to be as large as possible, as close to 1 as possible. Okay, so let's do this for linear contracts. And I think this could be another way of kind of arguing that, for example, linear contracts or other contracts, simple contracts, are good. So let's see how this would work out in the case of a linear contract. So here's a very simple example. So there are 2 actions, 2 outcomes. And it's actually complete information, right? So the first action deterministically leads to the first reward. The second action deterministically leads to the second. Rewards are 1 and 3, so the expected rewards are 1 for action 1, 3 for action 2. First action is for free, so cost is 0. Second action has a cost of 4 over 3. So notice rewards were 1 and 3. If I subtract the cost, then the second action is still better, right? Because 4 over 3 is less than 2. We also saw in the first half of the talk how to find the optimal contract here, right? So there are 2 actions, so we can apply what Imbal showed you. So first, we could just incentivize, of course, the first action. It's not costly, so we could just pay 0. We'd get the full reward, which is 1. On the other hand, we could try to incentivize the costly action. So how would we do this? So we would look at the outcome or reward with the minimum likelihood ratio, and then the payment formula. So we just pay for this. So in this case, it's outcome or reward 2. And then the payment would be just the cost divided over the difference in probabilities. So in this case, C2 over F22 minus F12, which is just C2 over 1, so 4 over 3. And then what we get, we're incentivizing action 2, and we get an expected reward of 3, paying 4 over 3. So the total would be 5 over 3, which is better than 1, so our optimum would be 5 over 3. Okay, so that's what you already know. So how about linear contracts? Question is, what can we do? So we have alpha, and then for different alphas, different actions will be incentivized. And what I found very useful in thinking about this, that's also in this upcoming EC paper, is to think about this in terms of an upper envelope, because this will immediately tell us which action will be incentivized. And I thought I'd give you this as a technical tool on the way. So what I want to do is, so I want to plot on the x-axis alpha, and then on the y-axis, I want to plot alpha times the expected reward of the action minus the cost. Okay, so as I go from alpha equals to 0 to alpha equals 1, I will go from minus the cost, right? So 0 and minus 4 over 3 to r minus the cost. So 1 minus 0 for the first action and 3 minus 4 over 3 for the second. Okay? And now this is really because of this pi idea that I showed you before. Right? So this alpha times r is really the expected payment to the agent. So that's really the agent's perspective that we are looking at here. So in particular, if you look at the upper envelope here, so action 1, action 2, then for each possible alpha, the highest line will tell you which is the best action for the agent. Right? So it's exactly giving you for each alpha what is implemented at alpha. And in particular, it also tells you if you want to incentivize action 1, what's the cheapest way of doing this? Well, look at the smallest alpha for which this is on the upper envelope. Right? So for action 1 here, this will be alpha 0, and for action 2, it will be alpha 2/3. Okay, now I can simply compute for both these values of alpha, what's my reward for action 1 and 2, and in this case, I've designed it in a way that this will be 1 either way. Okay, so in this case, whether I incentivize action 1 or 2 will only give me 1. The optimum one, I could get 5 over 3, so that's showing you linear contracts are suboptimal, and that beta can be at most 3 over 5. Okay, question is, I mean, this is just one instance, how bad can it be? Okay, and what we show informally in this upcoming EC paper is that linear contracts achieve good approximation, except in pathological settings where simultaneously the following happens. So we have many actions. We have a big spread among expected rewards of the actions, and also a big spread of action costs. Okay, so in particular, what are the kind of settings that I would call pathological? So here's one taken from the paper. So it's a setting where we set up the expected rewards so that they are 1 over epsilon, 1 over epsilon square, 1 over epsilon cubed, and so on. Similarly, the cost will be 0, 1 over epsilon minus 2 roughly, 1 over epsilon square minus 3, and so on, where I send epsilon to 0. So both rewards and costs are exploding. They are tending to infinity at different speeds. And this is a setting which will be bad. Okay, so let me make this precise. So what we show, formally, if you look at rho, so it's 1 over delta. So the worst case approximation ratio of an optimal contract and the best linear contract. Then what we show is that with n action, this approximation ratio is n, achieved by the pathological example that I showed you. And if we have a ratio of r between the highest and lowest expected payoff, we get a logarithmic in R approximation guarantee. And if you have the same for the cost, then it's also logarithmic in this ratio of the costs. Right, so we only are bad if all of the 3 are bad. Okay, and I should emphasize that we're thinking of this as a positive result because, I mean, this model has various ingredients. So hoping for kind of a, say, constant approximation guarantee across all these guarantees is maybe a bit asking for too much. What this shows you is that if you fix just one of the parameters, you get a tight approximation guarantee in that parameter. That's good. And also, if you look at the econ literature, then cases that are not covered by this, so where this is really bad, I mean, this doesn't really exist. So for example, if you look at a setting with effort and no effort, we're in the 2-action case, so a linear contract would be a 2 approximation. So for many economically relevant settings, this is actually giving you a good approximation. Okay, I should emphasize that all the upper bounds are with respect to the first best, so not just the optimal contract, but the optimal welfare, whereas all the lower bounds are with respect to the optimal contract. All of them are tight. And the lower bounds apply even under this regularity assumption of MLRP, which Imbal mentioned. They also extend beyond linear contracts to monotone contracts. Okay, so I think that there are many open questions here, so that this first analysis that we did only scratched the surface. I would say that this geometric view via the upper envelope is maybe the thing to take away here, but that there are many questions that you could ask. So the general question would be for which classes of contracts and under which assumptions on the setting can we get good, and I would say good is equivalent to constant factor approximation. So you could think about, for example, non-degeneracy assumptions or regularity assumptions that would imply, for example, that linear gives a constant approximation. We had a very strong benchmark here, so the optimal contract. You could think about imposing monotonicity in addition. So how good are linear contracts with respect to the best monotone contract? That's open. So there's a number of open questions, and I think generally what I would hope to be able to achieve here, or that you achieve here, is to repeat the success of the simple versus optimal literature in mechanism design. Okay, but instead of going into more detail here, let me mention one other direction, namely computational complexity, which I think could be maybe the most interesting of the 3 directions here. So Imbal presented to you the classical principal agent model. And as it turned out that if everything is explicit and you have one principal and one agent, then it's not really interesting, right? So you could just write down linear programs and solve them using linear programs. But I think that's not very, very satisfactory for several reasons. And one is that a principal could face more than one agent, then things become interesting immediately, right? So even if each agent has only 2 actions, things blow up exponentially. So the number of action profiles will be exponential. And the other thing, which I think is an interesting direction here, is that some part of the input could be given implicitly, like in the example that Imbal had with the agent that's running an online ad campaign for you. Maybe you want to be polynomial in the number of types, which is logarithmic in the number of outcomes. Okay, and I think there are many such models actually. For example, actions could be binary decisions. So you go to school or not, you go to university or not, you attend the seminar or not, you go to EC or not, and so on. So that's also exponentially blow up, where maybe you want to be polynomial in the number of decisions. Another natural model would be that outcomes are now sets, subsets of a ground set, and you want to be polynomial in that, and I think there are many others. Okay, I should mention, and some of the authors are sitting here in the audience, that, I mean, this is not completely new. So there's a very nice line of literature, and I think in particular a set of papers which was really way ahead of its time. So it's the combinatorial agency literature, which is already making good progress on some of these questions, in particular settings where a single principal interacts with more than one agent. So most of this work has focused on the case where each agent has a binary set of action, so effort and no effort. And I encourage you to look this up. What I want to do instead is kind of work out a bit of the details of the implicit representation models. And I want to show you some ongoing work that we've been doing on this, just to highlight the potential directions that this could go into. Okay, so this is, again, ongoing work with Inbal and Tim. So we consider the following succinct single agent model. So this is the ground set version of the problem. So we have me items, and then subset of items would be exponential in this. So we have m possible outcomes. So this is 2 to the power mu. What's the assumption on the rest of the model? So given an action I, we will include each item independently with a certain probability Fik. Right? So we have a polynomial in mu representation of the probabilities. And then for simplicity, let's just assume that the principal reward is linear. So it's, you have a reward per item. And then if you realize a certain set, your reward for that set is simply the sum of rewards for the individual items. Okay, and what this models is, for example, this example that Imbal had in the first part, as I mentioned already, with the agent that's running this advertisement campaign for you. So there we had 3 levels of effort, low, medium, and high. And we had the type of visitors that are attracted. So no visitor, just a general visitor, just a targeted visitor, or both. So you immediately see this kind of set structure here, I guess. So no one of them to the other one or both. And then this example was also set up in a way that has these additional assumptions that we need, namely that these probabilities here come out of product distributions of whether you reach a targeted or a general visitor. And the payoffs here were linear or additive, right? So 3 for just the general visitor, 7 for the targeted, and if both of them come, you get 10. And for the product distribution, I think that's easiest to see in the final example, where kind of the underlying product distribution would be as follows. So that if you take action 3, then you hit a general visitor with certainty, a targeted one with 0.6, so that you only see a general visitor would be 1 times 1 minus 0.6, so 0.4. That you just see the targeted visitor, that doesn't happen, right? Because you always see the general one, and you see both with probability 0.6. Okay, so in this case, which I think is a very natural assumption here, so you're running this campaign, you reach different groups of visitors independently with a certain probability. Can we do something, right? And of course, we could just use the vanilla LP approach, but this approach would be polynomial in M, right? And we would like to ask for more, right? We would like to be polynomial in the number of types, so logarithmic in M. Okay, so goal would be to use this succinct structure to exponentially speed up from 2 to the mu to mu the problem of finding the optimal contract. Okay, so recall. So I want to give you just, because we're just 5 to 7 minutes left, just very briefly the idea. So again, LP intuition will help here. So of course, that's what I said. We could just solve n instances of the min-pay problem. So that was kind of the naive approach to the optimal design problem. So given an action AI, we could try to find the minimum payment at which this action is implemented, right? So it minimize the expected payment subject to the incentive constraint that this action is preferred over any other action. But now they're polynomial in M, so exponential in mu many variables, and only n constraints. So one, I think, natural reflex here would be, can we somehow use the ellipsoid method by going to the dual? The dual is the following. So I don't want to explain in too much detail how this is derived, but again, we will have these lambda I prime variables for the constraints, and a bit of massaging of this dual gives you this form, where the interesting thing is that kind of the constraints that you would see, that you would need to solve for the separation oracle, have this ratio in here, which is basically a weighted sum of the probabilities of the actions other than I and the action I itself. Okay, so it's again solving some kind of min likelihood problem. But now this is for a combination distribution versus a product distribution. And it turns out that combination distributions in general are not product distributions, and this problem is hard. Okay, so what you can show is that solving this separation oracle exactly is NP hard. So this doesn't work. In fact, computing the optimal expected payoff in the setting in time polynomial in mu is also hard. Okay, so what can we do? And here's another, I think, kind of connection that you can draw to the AGT literature or inspiration that we took. I think a natural reflex in this setting would be to relax the constraints. Okay, so what if we relax the IC constraints? Can we get something? And there's no notion of approximate IC so far that I'm aware of for contracts. So here's one that we found convenient to work with and very natural. So it's the following. So given a contract T and an action I, we want to say that it's delta incentive compatible if the following holds. And let's do this carefully. So ignore the red part for now. So the left-hand side would just be the utility, so expected payment minus cost for action I versus the same thing for action I prime. And now what I want to do is I want to blow up the expected payment to action I, at least as a thought experiment, by multiplicative 1 plus delta. And only then you need to prefer I to I prime. Okay? So that's the beginning. And it turns out that in kind of normalized settings, as the ones you would study in mechanism design, this is just a delta IC with an additive delta. Okay, and what we show, that's the theorem that, or one of the theorems that we have proven so far, is that there's an ellipsoid-based algorithm that, given such a succinct contract setting with mu items and a parameter delta, returns a delta IC contract with expected payoff actually at least as good as opt in time polynomial in mu, which is what we wanted to achieve in 1 over delta. Okay, it will be exponential in n, so that's only working if you want for a constant number of actions. Okay, so how do we achieve this? So the idea is a fairly standard one, but it turns out to be or require some additional work in our case. So the idea would be to look at a strengthened dual where we multiply the left-hand sides by 1 plus delta, and then use a FP-TIS or design an FP-TIS for this separation oracle. And that's where the running time comes from, roughly, maybe the polynomial in mu and 1 over delta, but exponentially in n running time. So it's on a high level, the idea of the algorithm. Okay, of course, there are many other questions that you could ask. For example, what if there's a non-constant number of actions? We show several results in this working paper. So for example, that it's hard to find approximately optimal exactly IC contracts for any constant. We also showed that you can get constant factor delta IC contracts, and various other results. But there are also many interesting open questions left open. Okay, so I encourage you to watch out for this paper. Okay, so let me wrap up this part, and then afterwards the whole tutorial. So I think there are many interesting computational problems, which are, I mean, the fact that these exist, somewhat obfuscated by this classic econ approach of writing everything down explicitly. So this includes, I think, kind of sample complexity, black box access models, where I don't give you the distributions exactly, but maybe you can sample from them. What can you achieve? So this is also a very interesting question. I think this is very natural here, this approximation perspective, in particular looking at the upcoming and growing set of applications in e-commerce and the online world. And it's the good thing, it's mostly unexplored. So there's plenty of opportunity, I think, to do something useful here. All right, so let me wrap up very briefly only. So concluding remarks. So there are, I think, very important applications of contract theory. So contracts are everywhere, as Imbert said in the first half. It's increasingly moving towards e-commerce and online applications. So that's something where computer scientists naturally play a role. But even in the classical model, I think kind of the CS perspective, and that's hopefully something I could convey in this second half, could contribute something. So I've listed a few applications here. So freelancing, crowdsourcing platforms, startup funding platforms, blockchain, smart contracts, venture capital contracts, and so on. As I said, so we call this a new frontier for AGT, but actually, if you follow this classification, there's actually been some important pioneering works, in particular this combinatorial agency literature, which already started in 2006, but there's a whole lot of other work. So contract complexity, on incentivizing exploration, robustness we saw, adaptive design, so kind of a multi-arm banded work. So that's what I would call the first phase. But more recently, there has been, I think, this wave of works. So all of the second half of this page happened over the last year, where kind of basic contract design problems have been looked at upon by computer scientists. The ones highlighted in red will appear at this EC, so I strongly encourage you to go to these if you like the tutorial. I think there's lots of interesting work to do. And that's what I want to conclude with. Hopefully, your main takeaway from this tutorial is that there's actually a very simple mathematical model. Economists have worked on it, so it's very standard in econ. It's very fundamental, very central to microeconomic theory, and that the algorithmic perspective and our tools could really contribute here. Please do this. Go out and solve those problems. Thanks. I think we have time for questions. Otherwise, we are here for the whole week. And of course, there's much more work than I could cover in the second half that exists. So cool. So if not, thanks again for coming, and see you.